So in this video we'll be seeing how to write very simple basic IO driver for Windows. So before that, let's go and see some concept. So in WinObj tool from sysinternals, it will show us all the drivers and devices. Here we have these global. In this global we have the shortcuts. These are also called symbolic links. These are the symbolic links to the actual devices. So here we use these symbolic links to do the IO operations. So here we have the C colon. So C colon is a shortcut to the device hard disk volume 3. So we will if you want to create the file, you will use this symbolic link C colon, but the actual path will be the /device hard disk volume 3. So user mode programs will use these symbolic links to read and write to the disk. So in the device directory we can see all the devices, and here in the drivers we can see all the drivers. So what we are going to do is we are going to create a new device, and we are going to create a symbolic link for the device, and the user mode application will open and close the handle for the symbolic link. So before that, let's go and see the driver entry function. So this is the function that is exported from our driver. So our driver is similar to the DLL, which exports some functions. You can check that in the PE-bar or any PE parser. So go to the exports, and you can see these are the exports. Driver entry is the export, driver unload, and other two functions I have written. So these functions get exposed to the kernel, and it knows what to do whenever some event happens. So let's take a look at the driver entry, and it takes two arguments. One is the driver object, so the object of our current driver, and the second one is Unicode string to the registry path. So I can say this as registry path. So this registry path can also contain some driver related configuration settings. So I can hold down the control and click on this driver object, and you can see the information, the type of the driver and the size and device object. So we are going to create the device, IO device, and that pointer will be stored in this address. So in this member, if you create more than one devices, then these will be stored in the linked list. You can go to the device object, and here there will be a next device address member. It contains the address to the next device object, and so on. So that's how you can traverse through all the devices for the particular driver. And the driver start is the your loaded driver's entry point. So its base address, and the driver size, section, driver extension. You can also extend our driver. You can specify this as well, and the driver name, this is a Unicode string. So the actual driver name /driver, my driver name, and driver init is the our driver entry's address, so the address of the driver entry, and driver unload is the function address of the unload function. So whenever you want to unload the driver, that function gets executed. So you need to make sure this driver unload function is set, otherwise kernel will not be able to unload our driver. So the antivirus and EDRs will never give the address for this driver unload, so that their driver will be stayed will be present in the kernel. And the last one is major function. So this is an array of type pointer to the driver dispatch. So this is an array of function pointers, and here you can see the description: a dispatch table consisting of an array entry points for the driver's dispatch routines. So what are these routines? Means the events. So the IO events, whenever the application tries to create, open a file, read file, write file, that corresponding function address will be executed. The function at that particular index will be executed. So let's just write some code, that is driver unload. So what we are doing is we are specifying the driver unload function address. So this will take a pointer to the driver unload function. So driver unload is of type function that takes the driver object. So what we can do is driver underscore unload. So let this be our function driver underscore unload. So this function gets executed whenever our driver gets unloaded. So let's go and write this function. Remember, this function takes the driver object. So since we called this as underscore driver, now let's print something like driver unloaded. Okay, so whenever I try to, we have registered our function to this driver unload routine. So whenever our driver gets unloaded, this function gets executed, and any cleanup should be executed by this function. So let's go and compile this driver. So before executing, let's break into the VM and put a breakpoint at this test driver. So this is our driver name. We have registered as this test driver, and the function is driver entry. So we have seen the driver entry. So this is the driver entry, this is the function. So hit enter, and the symbol cannot be resolved, but it's still going to put a breakpoint in the future. So whenever in the future this symbol gets loaded, the breakpoint gets hit. So let's run this, and here let's go and start our driver. You can also put some print statements here telling that driver has been loaded. So let's run this, and I think we have hit the breakpoint. So we have hit the breakpoint, so we can go and view the disassembly. And this is very short routine because we have only single line of code. Now let's go and inspect this driver and the registry path. So in the x64 calling convention, the first parameter is stored in RCX and second parameter is in RDX. So later parameters will be stored in the R8, R9 registers, and then the parameters will be pushed on the stack. So R8, R9, R10, and then stack. So we have two parameters currently. So this driver will be stored in the RCX and this registry path is in RDX. So let's verify that one. So let's go and read the contents of RCX, and this is a pointer. So this should be pointing to the driver object. So here you can see whether this address is pointing to the driver object or not by verifying the driver name. So this is the driver name, driver test driver. So this is successful because this is what our driver name is. So that means the RCX is storing the driver object address. So the type of the driver and the size is in this decimal, and the driver start address. So this is the loaded our loaded driver's base address. So this is the base address 28C7000, 28C7000, and the driver size and driver name and the driver init. So you can see this is the actual instruction of our driver entry function. So the first instruction of the driver entry function 1330 and the driver start IO, driver unload. So you can see this has been set to null. So at this point we are here, we are not setting anything, and in the next step we are going to set the driver unload function address to this driver unload our function. So this driver underscore unload. So this is what it is doing, and this function also storing the contents of RCX and RDX on the stack. So I can go and say P. So RCX will be stored on the stack, and we are going to load the address of driver unload in the RX register, and this contents will be moved to the RCX plus 68. So RCX is pointing to the driver object, and plus 68 gives us the driver unload member address. So we are writing the contents of driver unload at this point. Okay, this VM is so slow now. Okay, let's put breakpoint at this. Okay, it is very slow. So okay, so let's hit again, and now if you read the contents of RIX, so this address should point to the driver unload function. So you can verify that using the X to verify that symbol, test driver unload, and you can see these are the same. And now we are copying into the at this point driver unload. Now if I go ahead and do the same, so DTNT driver object at the rate RCX, because RCX does not get changed in our code, so RCX still points to the driver object. So here now you can see the driver unload has been set to this driver unload function. So now we are just returning, so you can press continue, or you can also set breakpoint at driver underscore unload and then continue. So we are continuing from here onwards. Okay, now I am going to stop this. So our breakpoint has been hit, so you can see the pink line, and we are just calling the debug print. So if you hit enter, you can see the output. driver unloaded. Okay, so you can see the output driver unloaded from our debug print. So this is what just loading and unloading looks like. Okay, now what we are going to do is we are going to create a device using the IO create device function. So this the first I have already written this in our you can see I have already defined these function signatures linking this to NTOS kernel. So see the NTOS kernel. So let's go and create a device. So the first parameter is driver object. So we have got the driver object pointer from the driver entry function sent by the kernel. So that will be passing to this IO create device. So this will link the driver object's device object member. So here in this linked list, it's going to add our device. So that's why this driver object. So it needs to link the device to the driver, so that any IO operation to the device will be passed on to our driver. So device extension size, you can specify any number of bytes for your device object. So this is like a private address space for your device, and the device name. So before moving on to this function, we are going to create a Unicode string. So the device name should be the null terminated Unicode string. So we can use the RTL init Unicode string, and also I'm using another crate, that is OEB FSTR FSTR. So here we have the wide macro. We just need to pass the string. It is going to convert it into UTF-16 bytes. So device, so let's call this as my device /0. So in the malware development series, we did not use this crate. What we have done is we have encoded into the UTF-16 with the method .encode UTF-16, and then we have collected into the vector. So we do not have the vectors in the in our low-level driver development. We do not have the standard crate, so that's why we are using normal this crate to convert this into U16 bytes. So you can normally expand these bytes into U16, but it's going to take so much time. So I'm going to declare an empty Unicode string member. And I'm going to use RTL init Unicode string. So the first parameter will be the out parameter. So this function will write the contents to this variable. And second parameter is the bytes array. So the Unicode string. So let's go and call our function IO create device, and we can pass the driver object address and the extension 0. And the device type is So here we have the list of options for the device type. We are going with the file device unknown. So we are implementing our own custom driver. You can specify any of this, but let's just go with this file device unknown. And device characteristics. So we are going to specify this file device secure open, and the next one is exclusivity. So this exclusive, if you specify this as true, only one handle should be open to the device. So we are going to set this as false, and the function returns the device object. So we are going to pass a pointer to the pointer that receives the pointer to the variable that receives the pointer to the device object. So the 64-bit address will be returned to this device object, and the return value is status success on success. So let res is equals to, if res is equals to status success, then the device has been created, device my device. Then we are going to create a symbolic link. So remember, these user mode applications like functions like create file should only use the symbolic links. So if you go into the NT functions like NT open file, then they can use this this NT device name. So now we are going to create a symbolic link for our device. So you can copy the same initialization of the Unicode string and copy here and make this as DOS name or like dname1. So DOS name, so this can be like DOS devices. So you can also put double question mark, so that is also same for the DOS devices, and the symbolic name is my device 69. You can give the same name as your device name for the symbolic link. So for our symbolic link we are going my device 69. Sorry, here DOS name, and here it's dname1. So we have created our symbolic link, and we are going to use the IO create symbolic link function. So the first parameter is pointer to the buffered Unicode, that is user visible name, and second one is device name. So the first one is user visible name, and the next one is device name. So we can print something like device created. Okay, now let's go and say let res2 is equals to. So the result is also status success if the symbolic link has been created. So let's go and say print symbolic link created. Now at this unload function we are going to delete this symbolic link and also delete this driver. So we can do that using IO delete device function to delete a device, and IO delete symbolic name function to delete the symbolic name. So we can copy this and paste here and call the IO delete symbolic function and passing the DOS name, and also IO delete device. So here we need to pass the device object. Here we can see the driver object, right? So I have told you that this driver object contains the linked list of the device object. So list of the device object you can access the using driver dot device object. Remember, to remove all the devices you need to traverse through this list and delete each and every one. So the next device address will be 0 for the ending device object. So you need to traverse all the device objects until you reach the next device as null and delete the device objects. So up to now, let's go and compile our program. So there are some errors. File device secure open. So let's run debug view. I think we hit the breakpoint, so let's clear and clear. So let's run this, and we can see the device created and symbolic ring created. So let's exit this one, and here in the global, if you search for my device, so there is a my device 69 symbolic ring to the device my device. So here you can see the link to the actual device. The name is my device 69, and in the driver you will have the test driver, and in the device you will have the my device. Now let's go and unload the driver. You should see the deletion of these devices and the symbolic ring. So let's go and stop this, and you can see the red color, so stating that the device has been deleted successfully, and there is no test driver. And also if you search in my, so there is no my device 69 shortcut. So up to now we have successfully created a device and the symbolic link to the device. So now what we're going to do is, we are going to open the file. So I have already written a small code that uses the create file a function to this my device 69, and we will use the flag open existing because this should be existed. So if the file handle is invalid handle, we will report the error, otherwise we are closing the handle. That is the function. So before going to write some code that receives this create and the close request, we are going to see something called major functions. So test driver, so let's go and load our driver again. So in this we are at the driver entry. At the RCX we will have the driver object. So let's go and parse that one, driver object. So here I did not show you previously the major function, because now is the right time to show you the major function. If you click on this one, so here you can see all the indexes. So this index is corresponding to particular IO operation. So all of these indexes are pointing to some kernel default function, IOP invalid device request. So you need to actually overwrite these contents to your function addresses. So up to now our driver does not handle any open file or read file, write file or close file, any cleanup, etc. So this is just an empty driver. So whenever some application tries to perform some open or close to the symbolic link, so this function gets executed and we will get an error that invalid implementation. So there is no implementation for that operation. So what we are going to do is we are going to set these indexes. So these indexes values from these IRP. So IRP is the IO request packet. So this IRP contains the information about the current IO operation. So you can see the type and the MDL address. So this is important. In the next videos we will be using this address to read the contents from the application. So all the thread list entries and etc. are the other information. So in this particular IRP you will have the IO stack location. So that is the like a one part of the full IRP job. So IRP is a complete job. You can consider this IO stack location as the buffer that holds the information. You can see the major function, minor function, and the parameters that can be passed to the driver, and the device object and the file object. So this information will be useful for our driver to identify which function IO request is currently the application is requesting. So IRP MJ is major. So IRP MJ create, the value is 0. So that means you need to overwrite the address at this 0 index to your create and close. So in this video we are going to deal with the create and close. In the next videos we will be dealing with the read and write. So we have created the symbolic link. Now underscore driver dot major functions of 0. You can specify 0, but you can also say IRPMJ create as usize is equals to, you need to pass in the address of a function to execute. So we are going to create a function called IO create close to handle the create and the close request. So copy this and paste here, and IRP MJ close. Now let's write a function. That is IO create close. So you can go ahead and click on this, and this is the array of pointers to the driver dispatch. And if you go to the driver dispatch, this is a option of the function that receives the device object and the IRP. So if you go to the IRP, you can see the contents of this IRP we have just seen in the WinDBG. So my function, this function receives the parameters. So the first one is device object, ampersand mute device object, and the next one is IRP, and the next thing we are going to do is we are going to call one function, that is IO get current IRP stack location. So for every IRP there is an IO stack assigned. So in this it contains the type of the IO request and the parameters that are being passed to the driver, and the file object, device object as well. So this function routines returns a pointer to the caller's IO stack location in the specified IRP. So every function, every registered routine should call this to get the current IO stack location. So pass in the IRP PIO stack, so pointer to the IO stack. So up to now, let's go and compile and see. So now what we are going to do is, so we have one breakpoint at the driver entry. Let's also put a breakpoint at IO create close, the function we have just created. So let's run this and let's start our driver. Okay, now you can see the driver entry function. So here we are creating the device and the symbolic link. So actually you can run this one. We have another program that will try to open the symbolic link my device 69. So let's go and copy paste here. So now if I go and run this application, this application tries to open the handle to the symbolic link. Now as soon as let's once again unload the driver sc.exe. So before running the application, I want to show you how the major functions array looks like in the driver object structure. So stop our test driver. So we have hit the breakpoint. Okay, now let's parse the driver object at rcx. Okay, so here in the major function all are pointing to the default uh, routine handler, default dispatch handler. So let's put a breakpoint at the ending of our driver entry function. So let's put at this condition, and by now I think we have successfully set our the dispatch routine handlers. So let's see that one. So these driver object addresses are stored on the stack at rsp plus 50. So driver unload has been set and major functions, and you can see the two of them are different, so 0 and 2. So we have set the test driver, so you can see the 0 and 2. So 0 is the create and the 2 is close. So we have set to this function address. IO create close 21330 and 21330. So whenever some application tries to open or close the handle to our symbolic link, this function gets executed. So let's go and run this one. Let's see breakpoint. Okay, now we are good to go. Let's go and run this. So our driver has been running successfully. Let's go and run the program, and as soon as it tries to open the handle to the symbolic link, we are going to hit the breakpoint. So this is the function. So in this we are going to call the IO get current stack IP IO get current stack IO stack location. So let's put a breakpoint at this call. So let's continue, and let's go and continue. So in the RX register, you should see the IO stack location address. So you can see the RX register contains the contents, and it is being stored on the stack. So our variable, I guess. So let's go and So the major function value is 0 and the device object and the file object. So it also contains the device object structure address. And you can also see the RDX, the IRP value is stored in the stack. You can also read the contents. So pass this as IRP, and it contains the MDR address which is null, and IO status. So if you want to send some information to your user, you can use this IO status block. You can update the status like NT status success in this member, and any pointer, any information you want to send. So the number of bytes like copied, number of bytes written, so that amount of that information will be can be sent in this information. So our device object test driver. So you can also view the contents of the device object. So the type and the size, reference count is the number of handles that are opened to this device, that is 1. And the driver object, so the device object structure also contains the driver object. So and the next device is 0, so we have only one device created. And other important information, the device type 22, so 0x22 is the file device unknown we have specified in the IO create device function. And the stack size and the queue and number of threads and security descriptor and other useful information. So now what we can do is we can go and hit continue. So this breakpoint will also get hit second time because of the close operation, so the close handle. So let's go and continue, and you can see there is another hit. Oh sorry, my bad, that one is IRP. So anyway, so we can hit run. So again the next RAX, the next function is this is going to be executed, and the RAX contains the pointer to the IO stack location. So it's the same breakpoint we have seen in the previous call, the call to the IO get current IO stack location function. So IRP stack location, the function always gets twisted in my tongue. So let's read the contents of RIX, and these are the contents, and this is the IO stack location. And you can see the major function is 2 because we are closing the handle. So based on this we can try to code here. So what we are going to do is we are going to read 1 byte from this address. So here this we are going to read this value. So let major function is equals to as pointer to U8. So this is only of the size 1 byte major function. So match major function, if the case is equals to 0, then we are going to say print someone opened handle to our symbolic link. If the case is equals to 2, then someone closed the handle. So these two are the only values that will be sent to this function, because we have registered this function to only handle the create and close. So for every other thing you can just do null. So let's go and continue. Let's unload our driver. Let's compile our driver again. So we are just printing if based upon this major function. So our IRP request is completed because there is nothing open or close. There is nothing you can perform. For write file operation, you can read the contents from the user mode application. So we are going to do that in the next video. So our driver has been compiled. So let's start this driver. So let's run this, and you can see the device has been created and also symbolic link created. Now let's go and run our program. So you should see the statements: someone opened the handle and closed the handle, and you can see someone opened handle to our symbolic link and close it to our symbolic link. Let's go and unload our driver, and you should see the driver unloaded print statement. So that's all for this video. We have seen how to create a simple basic IO device driver, and we have created the device symbolic link, and we have specified the unload routine and also routines to the create and the close major functions, and finally we have printed the major function values.